So Theorem 3.1 was a one-step subgroup test, and the one-step subgroup test combined closure and inverses into one property that we had to show was true. Theorem 3.2 is a two-step subgroup test. It's very similar. It just divvies up inverses and closure. So let's read it together. We again have a group G, and we have a non-empty subset H. Then H is a subgroup of G if for every A, B, and H we have that A, B is in H, and for every A in H we have A inverse is in H. So this is not that much less than to show that something is a group. You show closure, you show that you have inverses, and you also show that your set is non-empty. That is also one thing that you have to show when you want to use the two-step subgroup test. The proof is given in the book. It's similar, or actually it uses the one-step subgroup test to prove the two-step subgroup test. You can read it in the book if you like. But we are just going to apply it in example 5. So in example 5, we are looking at a subset of the integers, and we're going to show that that is subgroup under addition. So under addition, and since we are going to go with under addition instead of using A times B, we are going to use A plus B as a notation. And that is what we are used to when we have an additive group, and this is what we're going to use as well. And A inverse is going to be minus A. So our notation for the inverse is going to be minus A, because that is the inverse of A in the group of integers under addition. All right, so let's apply the Theorem 3.2, our two-step subgroup test. Let's use that. 3 things we need to show. 1, non-empty. Our set H is non-empty. Second thing, we have to show that if A and B are in H, then A plus B is in H. And then the third thing we have to show is if A is in H, then minus A is in H. We're going to do this one by one. So non-empty. To show that something is non-empty, we just have to show one thing that's in there. We could go with all kinds of things, but an easy one that's often the one that will work quickly is to go with the identity. So the identity element is 0, and 0 is certainly in H, since 0 is 3 times 0, and 0 is an integer. So there's not even that much that we need to show. So H is non-empty. Okay. Secondly, part I. I mean, I called it 2 before, but it's really, it's I in our theorem. Let's choose A and B and H. Arbitrary elements. Well, since they're in H, they are multiples of 3. So we can write, let's say, A is equal to 3 times M, and B is equal to 3 times N. Very similar to what we have done before for some integers, M and N. Okay, then what do we do with them? Well, we got to add them. We have to show that the sum of those two things is also in H. So that is not that big of a step, but we do have to write it down. So A plus B is 3M plus 3N. And you might think at this point that you're done, but not quite. Yes, that what we see there is a multiple of 3, but to really convince someone that that's the case, we are going to factor out that 3. So 3m plus 3n is 3 times m plus n. And since m plus n is an integer, we can conclude that 3 times that integer is in H, because those are the type of things that are in H by our definition. So we've shown closure under addition. And then we can move on to think about inverses. So we choose again A and H. And we have to show that minus A is also in H. But if A is in H, then A is equal to 3m. Use the same notation as before for some m in Z. But if A is equal to 3m and m is in Z, then minus m is also in Z, because Z is a group and m is in Z, and so the inverse of m is also in Z. So minus m is in Z. So we have when we're looking at minus a, that is equal to minus 3m, but that is equal to 3 times minus m. And minus m was in Z, so 3 times minus m is by definition an element in H. And that was the second condition that we had to show. So by Theorem 3.2, H is a subgroup of G. In fact, not just G, in our case, it's a subgroup of the set of integers under addition.